So our next speaker is Tor. He just arrived from UK to enjoy the lovely weather in the Netherlands. And the talk is going to be about Turing. Turing.jl is a very well-known package in the ecosystem for Bayesian statistics, Bayesian modeling. And I personally use Turing a lot, just a baseline, because we also do Bayesian statistics in the university, but we use a bit of a different methodology. But Turing is great. I use it a lot, actually. So I'm very interested in the talk. Tor, the stage is yours, as you're ready. Please, a round of applause for our speaker.
Thank you, Dimitri. Hello, I'm Tor Fjelde. I work quite a bit on Turing.jl, which is a probabilistic programming language. I'm a PhD student at Cambridge, and I'm a research affiliate or associate or something like this with the Alan Turing Institute. And I spend a lot of time, too much time arguably, working on this project. So today I'm going to tell you a bit about it. Before we go into this, I'm going to tell you about Bayesian inference. I'm going to be quite brief, but hopefully it should remind people about what it is and give people somewhat of intuition about what it's actually doing. So, Bayesian inference, very quickly, is sort of the scenario where you have some real data, curly D, and you want to determine some parameters, theta, given this real-world data. And you're trying to inspect this probability density of the parameters given the data. And Bayes' rule tells us that we can decompose this into two components. Let me just get the laser pointer out. So here we have the likelihood, which is the probability of the data given the parameters, and this prior, that is the probability of the parameters that we choose before. And so because we do this decomposition, typically when in a PPL and also in mathematics, you write it in like this generative model formulation where you say like the parameters are sampled from the prior, and then the data is sampled from this likelihood. And so this is kind of the notation that you end up using. A very simple example is this, of this biased coin, where your data is a sequence of sort of heads and tails, and then you have like an initial belief that the coin should be roughly fair, meaning that, here we see that a lot of the probability mass is around 0.5, meaning like it's a fair coin. And then as we get more and more observations, we update our beliefs, and that's what you see on the lower right here. With the n here is the number of data points, and as we get more and more data, the posterior distribution over the parameters concentrates, and we recover the true parameters, but also with some uncertainty. I will give a brief warning, which is that people show these animations, including me, because they look very nice, and it gives the impression that you can just sort of update your posterior in this streaming fashion. Generally, that's not possible. If you do want these kind of settings, you need to work with certain models, and you need to talk to Dimitri, because that is what he works on. Another simple example is a linear regression example, where now you have pairs of points, so this input location x, and you have observations y, and here you have this your model is this linear kind of model, where you have some slope beta that multiplied by the input, and then you have some intercept alpha. Here we put some prior probability over these, and then we have the observations, the y observations, which are in some sense noisy, with this variance sigma. And then you can do inference over this, and here you can also see a nice animation of what it looks like as you get more and more data. The problem is that Bayesian inference is generally not, the posterior that you're interested in is not generally available in closed form, right? As that means that requires various approximations to actually inspect this posterior distribution. Typically, that is done using what's called Markov chain Monte Carlo, or variational inference. And these methods can be quite annoying and difficult to implement, in particular in a way where you can actually trust the results, because these are stochastic algorithms, and so, it's kind of, if you implement it yourself, sometimes it does the right thing, and then sometimes it doesn't, and it can be difficult to actually identify what's going wrong. And so then it's nice to have well-tested, battle-tested implementations of these methods that you can just, pick and choose from. So in summary, it's a principal way of incorporating prior knowledge into your simulator, like the model you have of your parameters. It allows you to quantify the uncertainty over the parameters that you're interested in, but it is non-trivial to do for interesting problems, both computationally, but also statistically. You kind of want the methods to be well implemented, so they're fast, but they also need to be statistically efficient in the sense that they can actually get approximation of the posterior that you're interested in rather quickly. And this is where probabilistic programming comes in. So like when I first heard about probabilistic programming, like many years ago now, I thought it was kind of like, what's the point of this? It seems like there's a programming language which is just fundamentally non-deterministic. I didn't quite understand like why this would be useful. And I think it's kind of like, it's not the best terminology. Effectively, like, probabilistic programming is really just about democratizing Bayesian inference, right? Because a lot of people who have data, they might be experts in epidemiology, biology, or something like this. They're not expert in the statistics part. And so it's really just about like bridging this gap and letting these people who have interesting problems and interesting data to analyze actually get access to these methods. And so what you want with the probabilistic programming language is just that the user should be able to write down the model fairly easily and iterate on it, change it, improve it. And the rest should be somewhat automatic. Like it should be able to do something reasonable. So the way to sort of view probabilistic programming languages, in my opinion, is just as a suite of tools that allows you to easily specify models and also perform inference and inspect this posterior distribution that you're interested in. And there are tons and tons of approaches to this. So there's some that are like the Bean Machine, PyMC, Pyro. These are in Python. They generally are based on sort of an underlying computational framework like PyTorch, NumPyro, and TensorFlow. That means they're very, very quick, but it means that, for example, you can't write naive for loops. You have to be a bit careful about how you write your model and stuff like this. Then there's Stan and Bugs, which are model where they have their own sort of domain-specific language that you specify your model in, and then they compile that to a lower level language, which is where the inference is performed. Say Stan's case, it's C++, for example. And so that creates a discrepancy between the implementation of the model, which is written in sort of this own DSL, and the actual inference language where the computation actually occurs. And that can be annoying because that means that maybe the packages, the functionalities you're interested in aren't actually available, and so on and so on. Then there's some like Anglican and Turing, which are implemented kind of where the DSL, the way you sort of specify a model, is done in the same language as where the inference is run. So Anglican is a PPL from quite a few years ago in Clojure. Clojure is unfortunately not a language that is like well suited for scientific computation, and so it hasn't really been applied as heavily as say maybe Stan. But Stan is sort of what we in Turing look at very often and think this is what we want to be, because they've sort of been incredibly useful for the scientific community. And so at this point, you ask, if I'm standing here, is Turing.jl the perfect PPL? Of course it isn't, it's far from it, but it is different in the sense that it is similar to Anglican. It's sort of the DSL, it's implemented in the same language as the inference happens. And that means that, which is Julia in our case, and that means that you get a lot of really, really nice interaction with the community, like the remaining packages in the ecosystem and so on and so on. As I said, it's Julia all the way down. There's not really restrictions on what you can put inside a model. It means that we sort of, the user is very welcome to shoot themselves in the foot if they really, really want to. But it means that it also compiles very, very nicely with the ecosystem. Usually at this point, I talk about Julia programming language, how quick it is, why it solves a two-language problem, and so on and so on. This is Friday, like so quite far into JuliaCon. I feel like you all know this at this point, so I'm not going to do this. But quickly, I'm going to give you a brief overview of Turing.jl. As said, it's a general-purpose probabilistic programming language. General purpose in the sense that it's not specialized on particular models. It's sort of very, very general in the models you can implement. Which models would actually be fast to run inference for, and so on and so on. And that's like a different aspect, right? But you can sort of implement whatever model you want in Turing. It's fully implemented in Julia, which generally means that it's quite approachable for users familiar with like MATLAB, Python, and R. And so that's like a lot of the people that we see are coming to us. They have no sort of Julia experience, but they start using Turing because they've been using Stan through R, for example, and then they try out Turing. That's also a way to get them into Julia, which can be quite useful. And it has been growing in popularity, I would say, particularly over the past 3 years. Obviously, like GitHub stars and like Google Scholar citations and so on, these are just proxies. They're not really accurate, but it gives you some indication of like people actually using it, which is quite nice. And I'll show you some example of this later. This is what a Turing model looks like. So here we sort of do using Turing like you do with any other Julia package. Then you define a model. The model is really just a function, like standard Julia function with this special tilde syntax. And this model macro, what it does, it just looks at the lines that have the tilde in it and changes those lines a bit. So like every other line in the model that doesn't have a tilde in it is left as is, which means that the user can do kind of whatever you want in there. You can put differential equation solving in there if you want to, which is a very popular application that people use quite often. And so it makes very few assumptions about the model itself. And so here you see this data sample from the prior. So there on the right-hand side, just like in the mathematical notation we saw earlier, the prior is a distribution, left-hand side is a random variable. Similarly, this curly d, which is the data, is sort of then a sample from the likelihood effectively. Then you instantiate the model. So this thing here generates two methods. One is for evaluation and inference, and the other is for sort of a constructor to define like this model type. So we make use of this here. We define the model, capture in the variable model, and then we condition this model on this random variable curly d being equal to some data that we have access to. This is very similar to what we write in mathematical notation. Capture this in a model cond variable, and then we can sample from this model cond, and that's how we sort of inspect the posterior distribution of this model. And so it's fairly straightforward. Mapping it from the mathematics, the generative model that we wrote down earlier, to this is quite simple. Here's a more concrete example with the linear regression that we saw earlier. On the right-hand side, you see the generative model. On the left-hand side, you see the implementation. And that's literally how it works. And so the nice thing here is that when you're, for example, working with people that aren't necessarily software engineers, or they're not like, super well versed in this, it's quite nice to be able to just have a mapping between the sort of the implementation of the model and the actual mathematical definition of the model. I'll point out this is a typo. This should have been in truncated normal, but otherwise it's the same. So, Turing.jl overall, the strength is that it's convenient and generally performant, particularly if you write the model in the right way. Really just thanks to Julia. It's very similar in design philosophy as Julia. It's sort of the idea is that we accept everything, we allow the users to do whatever they want, and then we kind of optimize when possible. And so we have like different modes of running the model. Effectively, one is faster than the other. And then models are just Julia functions. Distributions that we get from distributions.jl, they're just Julia functions. Sort of everything is just Julia, and so it works really, really nicely with the ecosystem. It does, however, because we make very few assumptions about the model, it means that certain operations that might be possible in other PPLs are not possible in Turing currently. There's nothing technically stopping us from doing this other than just developer time. But you can't, for example, do automatic modularization. It can be quite useful for certain models. And a naive implementation of a model might not be the most performant. So there's like some tips and tricks similar to how there's tips and tricks to how to write efficient Julia code. Similarly, there's for Turing.jl models. And so these are things that are like useful to be aware of. Before I go into this, I'm gonna have a sip of water because it's not wet enough already. So, Turing has been around for quite a long time. To show you briefly, but it started out when Julia was in 0.4. And the last talk about Turing.jl and related stuff, I think, was at JuliaCon 2022, so it's been quite a while now. I figured it was time for an update. I'm going to tell you briefly of like the history of it. We started out with Turing.jl in Julia 0.4. That was very, very different days. I joined when it was Julia 0.6, which is still very, very different from what it is today. And then that was happening in 2017, and this was his publication with Kai Su, Hongre, and Subin Garamani. And over the past 5-6 years, there's just been a lot of blood, sweat, and tears from PhD students, research assistants, and so on and so on. People that have been using Turing maybe for their research, and so they also contributed to it, or people who just wanted to procrastinate on their PhD and then decided to work on it. And some people have actually been sort of doing some research with it and so on and so on. But it's been very much like people just sort of working on it for a few years, and then maybe they have other responsibilities, so they have to move on, and so on and so on. And so now, in 2024, I'm very happy to say that sort of with the collaboration and funding through the Alan Turing Institute, we'll actually have people, sort of like Marcus here, working full-time. They're research engineers working full-time on the project for the next 3 years at least. And so then we have a lot of proper people, just really, really good software engineers actually working active on the project. And so that's quite like a big thing for us, just because now there's very, very capable people actually make it able to take this to like a stable state, basically. So what has happened over these few years? People are actually using Turing for real stuff. And that's quite exciting, in my opinion. So here you see some applications. One of these involves some of the people who actually worked on Turing. This is just a snapshot that I've taken from Google Scholar. And this comes from quite a few different disciplines. And this is kind of achieved sort of in the sense of what we wanted. Like it's people that have actually interesting problem, interesting data that they want to do some inference for. are using Turing to actually solve these problems. So this is applications that happen in biology, epidemiology, economics, neuroscience, and so on and so on and so on. And throughout the time, we've also gotten quite a lot of nice functionality. For example, back in the day, and this is still possible to do, if you wanted to condition a variable x on being equal to 1, like we saw earlier with this curly d, you would have to pass it as an argument to the model. And that's like for a lot of reasons. Like number one, it just seems a bit counterintuitive. The second thing is that it's just like, it doesn't really allow you to operate on the model very nicely programmatically, because you can't really inspect what is an observation, what isn't. So now you can sort of use this much nicer bar notation. And that means that you can also query the model and ask it what do you consider to be data, like what are observations. And then you can programmatically kind of remove things. So now you can sort of say, I want to fix this variable to be like x to be equal to 1. Then I can decondition it and remove the variable being fixed. And so that is quite useful if you wanted to actually like act on the model itself. Similarly, before, the really only thing you could do on a model was sample from it. But now you can also you can sample from it, but you can also using it like a sampler, but you can also just call random the model to sample from the prior. You can fix variables like the x, for example, which is similar to condition, but the log probability is not included. This is similar to sort of interventions in causal inference. You can call predict to predict from the model, and then you generated quantities is a way of extracting additional statistics or additional quantities from the model that you might be interested in, similar to like Stan's generated quantities for those familiar with that. These are just lists of operations, but they actually enable some quite useful things. So one very crucial aspect if you're doing Bayesian inference is that you kind of want to follow this standard Bayesian workflow if you want to be confident in your results. And I am just pointing to this paper by Andrew Gelman, Aki Vettari, and many other people, outlining quite an extensive document outlining a Bayesian workflow. Highly recommend it. But now this becomes kind of trivial to perform. I realize this figure is a bit small, but hopefully somewhere is readable. First thing, you define a model in maths, right? As we've seen before, that's what the first step to do. Then you define a model in Turing. So that's also quite like the translation there is quite easy to do. Here, you can perform prior checks, where now you can sort of easily fix parameters in the model, sample from the model that has the fixed parameters. Then you get your sort of a generated data from your model, given these correct parameters that you know of. And then you can perform inference on this thing again to check that you can actually identify the correct parameters that you see at the bottom here. It's like it's called like a prior check. And if you do this over and over again, it ends up being something called simulation-based calibration. This is quite a useful thing to make sure that the model, together with the inference algorithm, actually works, and you can recover, under the sort of the assumption that your model is correct, you can actually recover the parameters. And so because now this ran and this fixed and so on, this operations, like this workflow becomes quite trivial. Then, once you've done that, you condition your model on the true data, like the actual observation you have from the real world, perform inference, and then you can perform post-inference analysis, look at stuff like important statistics like R hat, R ESS, and also perform predictions using on the data. And then you rinse and repeat until you're happy with the model and the inference results you have. Additionally, you can now combine models. This was not something you could do before. But now you can basically take one other model and embed it into another model. And that is quite nice. It means like, because it's also all Julia, I could implement a sort of a package of epidemic models that are sort of working on like analyzing like epidemics. And then someone else can come along and they can do using epidemic models, and they can just take like, say, an SIR prior, for example, and then just embed that into their own model that they're now working on. And so it makes like sharing and reusing models like very, very trivial. Still have to perform joint inference over these things, but that's something we're working on. This is kind of, for example, a real-world example from a project that I was involved in, where we wanted to sort of iterate on a model, try out different varied ways of modeling, say the effective R number. This is like modeling COVID in the UK. And then we also had a model for latent infections. And then we had a model for the actual observed number of cases. And so then it was quite nice to just separate all these components into different models, and then we can just swap out, say, like the likelihood, for example, for a different likelihood quite easily. And it was like, when we were working on like a much larger project like this is like, becomes incredibly useful. Another thing is that in Julia, we use sort of these packages that do automatic differentiation. And we do that also in Turing. And we make and so when you, for example, want to do like use gradients, gradient-based samplers to do inference, like Hamiltonian Monte Carlo, you need gradients. And so because we're in Julia, we just use forward diff, reverse diff, all these packages that already do AD quite nicely. Problem is that before it was kind of difficult to exactly benchmark the model and figure out which backend you actually want to use. And so now you can use this very, very easily using Turing benchmarking.jl. Now you just call benchmark model, and then you get a bunch of you can pick the AD backends you want to look at and so on, and then you just can look at which one is fastest, and the one that's fastest, that's the one you pick. So this is literally what it looks like now. As that is also quite a useful thing, just makes the quality of life much easier. Now when you have a model and you're wondering which AD backend I should choose, just benchmark it and then you pick the one you want. Finally, there's also, like back in the day, when you run sampling, sometimes it can take days, which can be quite annoying if all you're seeing is just a progress bar telling you like how far along it's gotten. Now we still have that, but we also have logging to TensorBoard using TensorBoard thanks to Frames and other people. And this is what it ends up looking like. So here you see some sample statistics on the top here. Here bottom you see like the trace for the parameter that you're interested in. You get like histogram estimates of the parameters and stuff like this. This is also like quite useful if you have very, very long running inference runs and you want to kind of inspect how it's getting along. As I said, this is very much just like thanks to TensorBoard Another thing that has changed quite a bit with Turing since like its initial release is that it's no longer a monolithic application. So back in the day, it was kind of one single package. Everything happened in that package. Meant that like it was quite difficult to maintain. Much of it wasn't reusable, and so on and so on. And so we made like quite a big effort to just compartmentalize the different components. And that means that now, for example, Turing is just a shell around like a bunch of other packages, where the DSL is implementing a dynamic PPL. Samplers are in their own packages, but they implement this abstract MCMC interface. The nice thing about that is that you can use these sampler implementations that we work on and actively maintain without having to work on Turing. So if you think you can implement your model more efficiently than like you can write it in the Turing model, then you should do that and you should just use these samplers outside of Turing. Similarly, the hope is that this will also lower the barrier from people working on inference methods to actually making it to the user base that are of like PPLs who actually need these things, right? For example, you can implement your sampler in abstract MCMC.jl, and you can just run it on sort of standard log density functions. And if you do that, it's now possible to just use this in Turing.jl super easily. So that way, we should hopefully encourage more people that work in the inference part to actually just write them in Julia, and then once you've written in Julia, they're immediately available to the entire user base of Turing.jl for their day-to-day problems. Similarly, post-inference analysis is found in MCMC diagnostic tools and MCMC change.jl and so on and so on. This is quite like a useful thing. And so we're also, just so people are aware of this, like if you don't want to work with Turing.jl, there still might be like useful packages around that we're actively maintaining that you might find useful for your problem. So all in all, like this is basically what like the average user of Turing.jl sees, right? Just Turing.jl, this package. This is really more what the TuringLang ecosystem looks like. This is not actually quite it. There's probably a bit more of them. Here you see some orange highlighted packages, which are ecosystem packages that we don't own, but we contribute to them when we find bug fixes or we have feature requests and so on. And so we're super reliant on these packages. But these are actually not the packages used. Like this is more like the packages you use, right? Which is very typical for a Julia package. But they this is all with compat bound, so it's like fairly stable, and it's like we don't really have that many issues with it. But it shows you how like reliant we are on the entire Julia ecosystem, right? And it means that we can reuse components from that people have implemented once and implemented really, really well. We can just use that. And that is quite different from other PPLs, which are tied to some underlying graph computational framework, or they're working in their own DSL, so they kind of have to re-implement everything. And so we've had a lot of really, really nice applications coming out of this, basically. For example, there's hidden Markov models. Like we had a GSOC student called Jason Peskos who just sort of thought, hey, I want to implement this inference over a hidden Markov model. And I was like looking for implementation. We found hidden Markov models from Bill or Guillaume Dalle, I think. And he just put that into a Turing model, and it worked. Super nice. Similarly, differential equations is .jl. People just solve differential equations inside of a Turing model. This is probably when you look at research papers, this is really what people use very, very often, just because differential equations.jl is fantastic. So, briefly, what's next? It's not that much, actually, which is quite nice, standing here and be able to say that. There's some internal changes that needs to happen that will have performance improvements and also improve extensibility. Not super interesting for you guys. Now, one thing that we're really lacking is just documentation. That would be the #1 priority going forward. Will just be to document everything. For example, recently, TuringLang.org is the website that we have, and we've got a huge overhaul thanks to Shravan Goswami. And another big thing is that enzyme.jl, I mean, most people have probably heard about it. It's fast, and we've also seen that it can be quite fast when it works. And so now we're working quite actively with William Moses or Billy to actually make enzyme.jl work on kind of arbitrary Turing.jl model. And so that was something we're quite excited about. And maybe, hopefully very soon, Turing.jl version 1.0 should be released. And that should be, I want to give an exact date, but it should be fairly soon. This is obviously work that's been done over tons of years together with a bunch of people. So here are some, here are more people, and obviously everyone has contributed to Turing.jl and the Julia ecosystem as a whole. Thank you very much for listening.
Thanks, Tor. It's a great talk, great progress. Do we have questions from the audience? Yes.
Look behind you.
Hi.
Hi.
It's a bit loud. Yeah, thank you for this nice package. I really like Turing.jl, but maybe it's kind of not harsh, but support for state space models, and especially when you take in posteriors, is a bit verbose.
Yep.
Do you have any plans to maybe make it a bit user-friendly?
Yes, I mean, so there's actually there are people in our the TuringLang team effectively working on this basically, and actually they're specifically working on making state space models easy to implement. And we also have a person working on implementation for something called basically Julia bugs, which is a bugs version, kind of similar thing, re-implementation in Julia. In which case, it should be much easier also to make use of more information, because then you actually have access to the full DAG of the model and so on and so on. So there is actually work being done on this. I don't actively work on this, so I can't really tell you that much about it, but there is definitely people working on this specifically.
Yeah, cool. That's great.
Awesome.
Thank you once again.
Thank you.
Maybe a follow-up question from me. So you mentioned that the PPL in Turing is pretty flexible,
yeah.
But I imagine it actually also makes it difficult to analyze the structure of the model. Exactly. And maybe to find the conjugate relationships between variables to make it more efficient. So is there any plans to actually go in this direction?
Yeah, so exactly. So Turing.jl is we make really no assumptions about the model, and so we don't really have access to the DAG, for example, at least not at the moment. But there's one person working specifically on Julia bugs, which is a re-implementation of this old bugs PPL. And that case scenario, you actually do have access to the DAG, and then you can do conjugate, explode conjugate relationships and these kind of things. But that is more in the development stage, and so I wouldn't necessarily say that go and use that basically. But it is something that definitely that's being worked on.
Cool. Yes, we have more questions.
Yeah, thanks a lot for your talk. Great progress. I'm curious about the state of variational inference backend within Turing ecosystem. How is that doing?
It's not. It hasn't really been great. Yes, I worked on this as a GSOC student now 5 years ago. But basically, Kyrie here has been doing a lot of work on this actually quite recently. So he's been really taking ownership of this stuff and really working quite actively on it. So I would say right now it's not the best. The thing is also if you compare it to say PyTorch or these sort of Python-based PPLs, which are fundamentally based on these sort of neural these deep learning frameworks. This is kind of what they underlies them. They're also just better suited for doing variational inference, I would say, just because you generally typically when you do variational inference, I mean, it depends on what kind of families, but very often if you just want to throw something at it, often people use neural networks and so on, and then it's quite easier to do it with something where you have a deep learning framework. But so right now, I wouldn't say the support is the best. There's support for ADVI, and there's Seth has implemented Pathfinder, and there's nothing stopping you from implementing whatever variational inference methods you want. It's really just it hasn't been a huge priority. But as I said, Kyrie has been working very, very much on it like quite recently.
Yeah, thanks.
Do we have more questions? Yeah, we have more questions.
So we heard about RxInfer earlier today. Would you mind highlighting some of the strengths and the weaknesses and maybe how those two packages compare?
So I unfortunately arrived like half an hour before my talk, wading through the rain. But I have looked at RxInfer like quite a few years ago, so I'm not fully up to date on it. So I think he might be able to answer better on that. Yeah. But basically, like RxInfer does this thing where it's able to exploit conjugate relationships, as far as I remember, and it does it it means that you can very much do like inference in a very streaming fashion. So Turing.jl is more like you implement a model, you fix your data, and then you run this kind of expensive like inference algorithms for that particular data. If you want to update your posterior, unless you want to do like start like hacking on your own, you kind of just need to reduce the entire process again. While, if I understand correctly, RxInfer is basically like you just pop on another observation, then the posterior continues onwards, basically. And so I think that's a huge, huge difference, is that the conjugate relations is exploited in RxInfer, and that just makes it way, way more efficient, right?
Yeah, I want to say that this question was not staged, but I'm actually the main developer of RxInfer, so I can also add a little bit. From my perspective, I think Turing focuses on universality and user-friendliness, and it's really great, but it uses sampling-based methods, which makes it a bit less efficient. And RxInfer really focuses on efficiency and scalability, so it really tries to exploit the structure of the model, so we create an actual graph, and we do message passing. Is a completely different technique, differs from message passing, so it really depends on your application, and I think, yeah, you just need to decide what fits best. Turing is best, if you really want this universality, and RxInfer is best if you want to process data in a reactive manner as efficient as possible, that it also requires you to think a little bit more about how you define your model.
Thank you, both of you.
Thank you.
Do we have more questions? Okay, then we close the session. Thanks very much, Tor. It was a really good talk, really amazing progress.